So what I want to do, as I indicated, is to discuss identification problems in the context of social interactions models. And the way that I wanted to proceed was to start with the workhorse model of social interactions, which is the so-called linear means model, which is and I will talk about it as a linear model itself, that it will be separable in certain variables. And as I indicated, the idea is going to be that we have some outcome of interest. It's going to be determined by three types of variables. One set of variables indexed at the individual level. And so that's the idea of parent and a second set of variables will be indexed at the group level. And so that would be the idea for something about the neighborhood I grow up in that has an effect on me. It could be the average of the parent's characteristics. It could be something else. And then the third is going to be that there's an interdependence between my behaviors and the behaviors of others. And so the idea in the linear and means model, the average and the mean, is that I care about the average, or I respond to the average behavior of others. Now, if you think about the micro foundations for that, Larry already gave them to you. In other words, if you have for example, if you have a quadratic loss function that says that I am penalized in terms of my utility by the squared deviations of my behavior from the average of others, and the expected value of that deviation, the first order condition gives this to exactly this type of behavior. All right? And so the identification question is, can one, given, one way to say it, infinite amounts of data, or put differently, given the joint probability descriptions of the omegas, the x's, and the y's, given those joint, that's what the observables give us at the end, are probability statements about their relationships, can one uniquely choose the values of the parameters. All right, what distinguishes identification in regressions, as you well know, from others is, again, the sufficient statistics for the probability descriptions are the second moments of the data. And so that's where we get classical identification results. All right? And so where I ended the last lecture was to emphasize that at least one of the ways that one proceeds constructively is to take a stance on the source of subjective beliefs. And I would rather just say that latent variables called what I think about the world, there's some consistency imposed in the logic of the model. And so the notion of a Bayes-Nash equilibrium, or we don't want to say macroeconomics, rational expectations, is that the subjective beliefs that individuals have about the averages in the population are determined by the mathematical values of those expectations. All right. And so where I left off the last lecture was to emphasize the issue is to take a stance on the relationship between the latent variables called beliefs and the observables we have in the system. That's going to give us the purchase to actually talk about identification. All right, so what does it mean to say that there are statements about social interactions in the world? It's a statement that, conditional on knowing things about individuals at the individual level, information about higher levels of aggregation, about social aspects of the environments in which they live, have marginal explanatory power. And so in this model, the social interactions idea is simply a statement about coefficients. In other words, it's a statement that either D or J is non-zero. Now, to be clear, the identification question is slightly different, which is asked whether I can distinguish them uniquely given the data. But the thought experiment is to say if they're non-zero, then we have a claim, a proposition about the role of social phenomena. All right. That said, one of the important dichotomies in the literature is the distinction between D and J. D is the set of parameters, the invariant objects that link characteristics of the people in a social structure to each individual. So that's the idea that the average parental income has an effect on me. And so that's often called a contextual effect. In contrast, J is called an endogenous effect because it is measuring how behaviors themselves are interdependent. And so the key distinction intuitively is that if we're thinking about contextual effects, we take the characteristics as predetermined. Whereas when you think about endogenous effects, there's a simultaneity in the relationships. That's just a simple way of saying that whatever the distribution of role models in a community, I don't think the children's behavior changes the role models. In other words, different outcomes for children do not change the distribution of college degrees amongst the parents in a community. In contrast, if I'm thinking about the behavior of children in a classroom or adolescents in a school, there's a simultaneity that's going on. And notice that in contrast to the classical way we talk about simultaneity, here simultaneity is mediated by beliefs. So in other words, in this structure, the sense in which you and I are interdependent in our behaviors is I have beliefs about what you're going to do, that influences what I do. You have beliefs about what I'm going to do, that influences what you're going to do. And so the simultaneity is not in the sort of standard regression simultaneous equation sense. It's mediated via the way that beliefs are formed. Okay, so that's a little bit of just a nuance to be aware of. All right. Now, this is a very important point. In the original formulation of the linear and means model, there was an additional restriction placed on the relationship between the contextual variables the contextual variables y and the individual variables x. Specifically, the Mansky formulation made the following assumption. It assumed that the contextual variables are the averages of the individual level variables. Everybody with me? So if I say to you, your parents' income has an effect on you, that required that the model also say that average parental income in your group has an effect on you. If your parents' educational attainment has an effect on you, the average of the parental educational attainments in the community has an effect on you. So in other words, this was an implicit, the formulation I gave you, in fact, is a little bit more general than the one that is the basis of the literature. Because I didn't take a stance on the relationship between individual and social variables. That's going to turn out to be very important. In other words, that the analyses in the original literature had a one-to-one relationship between them. Right. So that's kind of that's the model we have. Now, here are some boring equations. In other words, I'm going to start off with taking a stance on the nature of the unobserved heterogeneity. After all, when you learned basic econometrics, how were you taught it? I claim this is how you were taught it. You wrote down a model that said y equals x beta plus epsilon. You then made an assumption, and that was x and epsilon are uncorrelated. In other words, they were orthogonal to each other. That was what I call the nice error assumption. That takes a stance in the relationship between the observed heterogeneity and the unobserved heterogeneity. Once you did that, then you could focus on the condition for identification of beta that had to do with the linear dependence of the x's. Had I said to you the x's and the epsilon were correlated, then it was a completely different exercise. And so in thinking about identification in social interactions models, we go through that same set of thought experiments. Thought experiment number one is we have strong prior knowledge of the relationship between the observable heterogeneity and the unobservable heterogeneity. And it takes the form that I said was quote-unquote nice, which is they are orthogonal to each other. Once I have made that assumption, then I can think about the identification problem in a very classical way. And what I mean by that is, going back to our equation 1, that just looks like that's just a regression, isn't it? So if I ask you, can I identify C, D, and J, under the assumption of orthogonality of the observed and unobserved heterogeneity, that's equivalent to saying orthogonality of the regressors to the epsilons, you know how to proceed, don't you? You would say that identification is determined by the presence, whether or not the variables in that system on the right-hand side are linearly independent or linearly dependent. Okay. And so that's going to be the first set of discussions we have, is under what conditions does identification hold under the orthogonality assumption for the unobserved heterogeneity. Then we're going to back off and say, well, let's relax that assumption and ask how would we proceed. And so the first, kind of a general background message is an understanding the identification problem for social interactions. We start with linear models, and amongst the many advantages of, well, there's actually an advantage and a disadvantage. The advantage is you already know abstractly how to think about the identification problem for linear models, don't you? And it has to do with the linear dependence of, or independence of the various regressors. So the advantage is going to be we can bring those intuitions to bear and very easily solve for the conditions. The disadvantage, strangely enough, is that linear models exhibit failures of identification that do not occur in their nonlinear analogs. Everybody with? So I'm actually making a claim that the identification problems are, in some sense, quote unquote, harder if we're living in a linear world than a nonlinear world. So let me give you, is everybody with? So I made a, that sounds strange, doesn't it? So why would linearity be problematic? Here's a way to think about it. If I said to you that I have y equals x beta 1 x1 plus beta 2 x2, what's going to kill identification is if x1 and x2 are linearly dependent. What if they are functionally dependent but not linearly dependent? In other words, think of a model where y equals x1 beta 1 plus x1 squared beta 2. That model's identified, even though there are functional dependence between the regressors of that. And so that's a hint to us. In other words, that some of the failures of identification are specific to linear dependence, not functional dependence. Does everyone see that? So that, if you run after all, you could run time. You could do time series models that have time and quadratic terms, etc. Those models are all identified, even though the regressors are functionally dependent on one another. The fact that functional dependence, if it's nonlinear, is consistent with identification is actually a hint that nonlinear models are going to exhibit identification properties that are sturdier than linear models. All right, everybody with me? So we actually, so the identification question. If I say to you this model is identified, what I'm saying to you is that its regressors are linearly independent. What are the regressors in the model? The x's, the y's, and m. Why did I say uh-oh? Because m, unlike x and y, is not observable. That's the reason that there's a distinct set of questions for identification in rational expectations models. But notice, and so this is how I want you to think about the problem. Comment number one, if m were observable, then we would be back in the world of the standard identification question. And that is, are the regressors linearly independent or not? So with that as background intuition, how do we think about identification in this model? It's very simple. We exploit this equation. In other words, if I say to you that m is linearly independent, it is not observable, that's fine. If I have a theory of what determines m. Everyone with me on that? By the way, what is m? Oh, and where do I have pens? They're over here. That was very intimidating. M is the expected value of omega bar given the observables. Everyone with me on that? That's its definition. That's what it means to say, I have imposed a Bayes-Nash notion of rationality. Can I construct this? If I give you data on omega bar, x's and y's, can you tell me what the expected value is of omega bar given x and y? Of course you can. That's a regression. You would regress omega bar on the x's and the y's. Therefore, even though m started off unobservable, if I assume rationality of the type that I've described, I have implicitly made m observable. Because as the econometrician, I literally can construct it. It is nothing more than a linear projection of the realized omega bar on the information set of the individual agents, and that information set is the x's and the y's. All right, so now I've just revealed the secret, the state secret of rational expectations econometrics. when you impose rationality of this form, what you've implicitly done is said the unobservable variables that are the expectations can be constructed via reduced form linear projections. All right, now I could have written down much more sophisticated econometric models in which I have expectations today, dependent expectations about the future, so on and so forth. The logic of the identification problems would still be exactly the same. Whenever you impose rationality of this type, you can replace the latent variables for the beliefs with the linear projections of the realizations on the information sets of the actors. Please.
I want to point out that anytime you estimate a Nash equilibrium relationship, you're doing exactly the same thing. Because what is Nash equilibrium? You're saying that people have beliefs, they best respond to their beliefs, and their beliefs are accurate. So what are you doing? You're constructing the beliefs from, you know, which are latent from the observable data. This is implicit,
and that's a
very generally.
Yes, that's a very important point, and to see the distinction between that and the model that we're working with, I didn't put the expected value of this given the actual omegas. After all, if I knew the omegas, if I could observe the behaviors of others, then I would form my belief about omega bar given the omegas of others, and that's a very easy calculation. The expected value of omega bar given omega bar is omega bar. and so all that's happening is every time you specify an information set, you're altering the way you construct that conditional expectation. You can move all the way from complete information to
that's really the way to understand it, that when you move from complete information, the construction is just placing the, you know, the latent variable with the observed. But in a Bayesian game, of course, you're doing something, you're doing something more, but it's still the same principle.
Okay. So you see how useful it is just to, you know, make these, you know, these intuitive observations. Is now I have a well-defined way of asking the identification question. From basic econometrics, you knew that identification, if the regressors are observable and they obeyed the nice assumptions, came down to asking, are the regressors linearly independent or not? So we have one set of regressors, they're called X's. Those are the measures of individual characteristics. We have a second set of regressors called Y's. They are group level characteristics. What is the value of M? Well, the value of M by definition is the expected value of omega bar given the X's and the Y's. But we need a formula for it. After all, I don't know if that conditional expectation is linearly dependent on the X's and the Y's, do I? I just know it's another variable. So that's why we do this calculation right here. What is the expected value of behavior in a group? So the way to think about it is, I take this equation 1. This is basic rational expectations calculations. I take equation 1 and I take the expected value of both sides. The expected value of the left-hand side is by definition M. In other words, if I have a group of people, the expected value of a typical person is the expected value of the average. I don't need to distinguish them. The expected value of the right-hand side is going to be expected value of constants is a constant. The expected value of CXI is CX bar. If I don't know the value of X, the expected value of CXI is the expected value of X, which is simply its average in the population. The expected value of DY is by definition dy, because we know what. That was part of the information set. The expected value of Jm is Jm. The expected value of their expected value is the expected value. Lo and behold, we have an equation. The expected value of M is equal to K plus Cx bar plus dy divided by 1 minus J. I just take the original behavioral equation, I take the expected value of both sides, I rearrange terms, and that gives me explicitly the relationship defined here. And it's very intuitive. The expected value of behavior, the average behavior in the group, is determined by the average of the individual characteristics, those are the X's, and the common effects on everybody, which are the Y's. Now, you take linear combinations of them, and those linear combinations are determined by the parameters of the model, right? so now so we now have the identification question. Is M, which equals that's the rational expectations assumption, linearly independent of X and and of Y? Okay, before I go on, is everyone clear? This is the identification problem for a linear social interactions model. And so what I'm concerned about is the dimensionality of this space. In other words, there's R plus S plus 1 regressors. I need the dimension of the linear space that they span to be R plus S plus 1. That's what it means to be linearly independent. So identification is going to require this. Notice here's a necessary condition for identification, and that is that the dimension of X and Y equals R plus S. Okay, that's a trivial statement, isn't it? After all, I need the regressors to be linearly independent. It better be, if I take the first R plus S of them, they're also linearly independent. All right, so in other words, we know the first condition, obviously, is the contextual effects have to be linearly independent of the individual effects. Everyone with me? Now, that's true in any regression model. Why is it of interest here? Consider the following. What if there is perfect segregation of people by groups, and each Y is the average of an X? Everyone with me? So in other words, everybody is affected by his or her family income and the average income of the neighborhood. If I perfectly segregated people by income across neighborhoods, so there's no heterogeneity within neighborhoods, would this condition hold? No. Under perfect income segregation, in the example I gave you, it would be the case that if I know your income, that's also the average of the neighborhood. Okay, so there's an example in which we see that the level of segregation is going to have some effect on the identification problem. Okay, and so if you think about it, that's kind of an intuitive thing, isn't it? If I perfectly segregate people, how could I tell whether it's a group effect or an individual effect? Because if I know one, I know the other. Okay, so this is something to keep in mind, an idea there that's useful in thinking through when we will have identification. So that's the idea one. Then idea two is, if I take this linear space and I augment it with with the M, does that raise the dimension? And so the answer to that question is determined by the properties of phi. So in other words, I know that when I take the XY space and I add M to it, I've added a new regressor, a new variable. The question is whether I change the dimension of the space. Now, if we think about that, I'm just going to ask a counterfactual. Let's suppose that C was 0. Everyone with me? If C were 0, then M would be linearly dependent on the Y's, right? Well, if M is linearly dependent on a Y, then this can't happen, can it? If I add a linearly dependent regressor to X and Y, that doesn't change the dimensionality of the space. That's a thing to be worried about. And that's what, so in the so-called reflection problem, this is also the simultaneous equations question, isn't it? M is endogenous. It's linearly dependent on the other regressors, then adding it to the system doesn't change the dimension of the space, and identification could fail. And now we have an intuition that says that, well, maybe a problem with identification is that M and Y are going to be closely related. After all, the contextual effects, the common effects to everybody, simultaneously change the average behavior. That's creating a link between those regressors. That's idea number one. On the other hand, let's assume that C isn't 0 anymore. Now we see why identification might hold. After all, the average of the X's is moving M around. And that isn't and the average of the x's may not be the same as y, and therefore it's possible for m to move around when y doesn't move around. That's linear independence. So that's the key condition. If you think about linear independence, it's a nice phrase that summarizes things. But the question is whether or not I can move some of the regressors around without moving the other ones around in a linear relationship to them. The possibility for identification in these models derives from the fact that x bar is moving m, even along with y moving m. Everybody with me on that? So that's the condition that we have to think about. And so now, actually, let's just stare at this a little bit more. And what we see is the following. The condition for identification in linear social interactions models is that this space has dimension r plus s. That's the one you knew from textbook econometrics. I need the original regressors, the observables, to have full rank. What gives the identification problem a distinct flavor here is the second condition, which is the expected value of the average choice. If I augment that space with it, it raises the dimension. Here's a special case. What happens if x bar g equals yg? Is this possible? No. If x bar g equals yg, then m is linearly dependent on the y's. Therefore, augmenting the space with m can't change its dimension. So under this special case, identification has to fail. That's a non-identified model. Everyone see that for the special case? What would give us identification is if x bar can move around without y bar moving in concert with it. That would let m move around without a one-to-one, without a linear relationship to the y's. When y equals x bar, you have linear dependence and identification fails. We have just given, that is the reflection problem. So to understand the history of the literature, in the Mansky 93 paper, he assumed x bar equaled y. Remember I said through that, that assumption matters. This is why it matters. Once you make that assumption, identification fails. Okay, and that is what is known as the reflection problem. The general condition for identification is, in other words, the conditions for identification in linear and mean social interactions models are those two dimensionality conditions. Under the assumption that was made in the 93 paper, the second one of the conditions can't hold. And that's why the paper had a negative identification result. And that created the, if you'll forgive me, the folklore that these models are not identified. We now have a hint here, don't we, as to what we were going to need for identification. Here's a necessary, everybody following the logic of what I've had to say? I need m to be able to move them around in a way that's not linearly dependent on the x's and the y's. That's what the key is going to be for identification. M is dependent on x bar and y, and therefore I need the x bars to be able to move around in a way that's not linearly dependent on the y's. So now we have an insight into the necessary condition for identification. When I write down a linear social interactions model, I need to be able to identify a variable x whose average, x bar, is not in the original model. After all, that the condition for identification fails said that for every x, x bar is a y. X bar is in the equation. When there's a one-to-one map between the x's and the y's, there does not exist an x whose x bar isn't in the model. That's a failure of identification. By implication, A necessary condition for identification is that there is an x bar in the original model, actually an xi in the original model, whose x bar has been excluded a priori. Did everyone see that? I need to have x bar moving around the m in a way that's distinct from the effect of the y's. Therefore, for that to be true, there must be an xi whose associated average isn't already in the y's. So there that is. So that's the constructive way to think about identification. When you specify a linear social interactions model, you need to have a priori a variable at the individual level whose group level average is not included in the equation. That should remind you of something. It's like an exclusion restriction in classical simultaneous equations. In the social interactions literature, it has a very specific interpretation. I need the expected value of the averages to move around in a way that is not determined by, linearly determined by the y's. The way that that can happen is that there's an x bar that's moving the m around that's not already included in the y's. And so that's a form of an exclusion restriction. And that, of course, should echo with you, because when you learn identification in simultaneous equation systems, you learn the following. The reduced form does not identify the structural parameters unless you had prior information on the structural parameters. That prior information came in two forms, didn't it? That linear combinations, basically all came, they came down to linear constraints on the structural parameters. I might tell you two structural parameters sum to one. Those we typically don't. But the ones we really like are the exclusion restrictions, that a certain parameter equals 0 a priori. Here, the analogy to an exclusion restriction is that there's an x bar that does not appear as in the list of variables that I call them y's. Before I go on, does everyone understand that's the algebra of the identification problem called the reflection problem. It is exactly analogous, and in fact, it is a form of the question of identification in simultaneous equations models. Only difference, the differences between this model and a simultaneous equations model comes down to the following. Okay, before I go on, does everyone understand what's going on in the system? If the model is identified, I need an x whose x bar does not appear in the equation. If I don't have such a variable, then m has to be linearly dependent on the y's. So that's the identification condition. Now notice, going back to this equation 1, suppose that that was my equation. I said that my behavior depended on stuff and it depended on my beliefs about the average behavior of others. Classical simultaneous equations models would not have the beliefs about the behaviors of others. What would have appeared there? The actual behaviors of others. So in other words, when you learn simultaneous equations, the way we would have done it in an environment of behaviors, you would say my behavior depends on your behavior, not my expectation of your behavior, your actual behavior, so on and so forth. So the distinction between these models and classical simultaneous equations models, the first one is that because expectations mediate things, we don't say that each behavior depends on the realizations of others. We say that it depends on beliefs about the realizations. Everyone with me on that? But you can see that can't change the identification problem. Why? How does two-stage least squares work? If I say that your behavior depends on her behavior, and I need to use instrumental variables for you, what am I doing? I replace in the equation for you his omega with the expected value of his omega. That's all two-stage least squares does. So in other words, a way to understand classical simultaneous equations is you have a set of endogenous variables. Each endogenous variable depends on the other endogenous variables. To do instrumental variables, two-stage least squares is to replace each of the right-hand side endogenous variables with its conditional expectation. So in that sense, it's exactly the same model. The identification conditions are the same. I just didn't go through the artifice of saying I need to instrument for things. They were already instrumented for implicitly when I used expectations. All right, so in that sense, there's absolutely no difference between this and a simultaneous equations model. The other difference between, there is, however, the following, and that is that notice, everybody with me on that first point? If I put omega bar there, I would have to come up with the instrumental variable's estimate of omega bar, and I would substitute that in. Then I would do identification analysis for that. But that's the instrumental variable's instrumenting omega bar is constructing M. It's exactly the same thing. So in that sense, there's nothing new under the sun. Second comment. Notice that in this particular simultaneous equation system, a very strong assumption is made about the relationships of the endogenous variables. The assumption is that I react to the average of the endogenous variables. I don't have any intensity differences. I know Hosni better. I don't get to put a bigger weight on him than you, who I don't really know. In this model, everybody gets the same weight. So in that sense, the reflection problem is the classic simultaneous equations problem under a special assumption about the relationship of the endogenous variables. And the special assumption for the relationship of the endogenous variables is that everybody is given the same weight. And that's why there's not, in that sense, it's just a special case of the broader question. All right. Everybody with me on those ideas? So if I write down a linear social interactions model, I wish to distinguish individual effects, contextual effects, and endogenous effects. The key is I must have a variable, an individual level variable, whose group level average I have excluded from the system. That's an exclusion restriction. So where do those come from? Notice I changed the conversation in a qualitative way. What I start off is just giving you some mathematical results. Because if you think about this social interactions model in this form, they're really just linear simultaneous equations models where expectations are imposed directly as opposed to via instrumental variables. That was an observation. Then we have the observation that we know how to do identification for linear simultaneous equation systems. In this particular environment, the exclusion restriction that is necessary is that the x bar is excluded from the set of y's. That was the assumption that I would need that as a necessary condition for identification. And all of those statements, I said, they're mathematical, they're algebraic statements. They're theorems. When I said I changed the conversation, I asked you a new question. Where do you get it? On what basis do I exclude a variable? Everyone see that? So if I write down a model and I say that parental income affects children, individual parental income, if I want to identify social effects and contextual effects, it would help me if I could say a priori that average parental income does not affect. That doesn't sound very persuasive, does it? That's the point I want on this table. Whenever we write down statistical models, we're going to have a set of conditions. And I'm going to call them mathematical conditions under which the model is identified or the model is not identified. The challenge for you as social scientists, as economists, is to translate the mathematical conditions for identification into behavioral statements. So if somebody wrote down a model, if I write down a model, they look mathematically, it's identified. The way you evaluate the model is not to ask, did I violate the conditions of the theorem? Presumably I didn't. I was honest. But the theorem says it's identified. The way you evaluate it is the exclusion restriction credible? If I've written down an environment in which I say my behavioral assumption is that average parental income does not affect children, but individual parental income does, that may be a good assumption, may be a bad assumption. But that's how you evaluate the papers, on the credibility of that assumption. So when I was pounding my fist on the table in the lecture yesterday and said it is extremely important to read other literatures, one of the reasons is that that helps give credibility to the exclusion restrictions. The exclusion restrictions are things that they have to do with information that's outside the model that you bring to the model. And that's the hard, maybe the hardest thing in empirical work is making those types of judgments. Okay. Now, before this lecture is over, I promise you I will give you an example of an x, whose x bar as a matter of theory, should be excluded from the equation. In other words, there'll be a case in which identification holds. But in general, those are going to be complicated judgments. So that's really the message I want on the table, is to understand the reflection problem is not a unique or distinct problem in identification. It is the problem of identification in simultaneous systems. It happens that in linear and means models, the identification problem for simultaneous equations has two nuances. One of them is that we work with the expected value of the endogenous variables as opposed to the endogenous variables themselves. That is a distinction without a difference, because instrumental variables always implicitly replace endogenous variables with their expected values, equation by equation. The second thing is that the logic of the linear means model restricts the weights that you assign to the endogenous variables. I can assign the same weight to you as to you as to you as to you, and that's not something you do in an arbitrary simultaneous equation system. But modulo those two nuances, the identification problems are exactly the same. All right. Are there any questions? All right, so what I went on the table was what I called the key logic of the reflection problem. What I want to now do is consider variations of the linear and means model and see whether or not identification conditions change. So in other words, what we have on the table is in the baseline linear social interactions model, identification is contingent on prior information. In other words, if it is the case that every x bar appears in the set of y's, identification fails. That's the reflection problem. But it doesn't mean that identification has to fail. It means that I have to have a reason for excluding one of the x bars from the list of y's. What I want to now do is ask the following question. Suppose I consider models other than the linear and means model. Does identification change? Where I want you to be is not happy or sad, in other words, in terms of identification. What I want you to see is identification, in this case, was contingent on prior information. Just as identification in any linear simultaneous equation system is contingent on the assumptions you make about the regression growth, about the model coefficients. No assumptions, no identification. So first, I want to ask this question. I've emphasized there is a isomorphism mathematically between linear simultaneous equation systems and linear social interactions models. We exploited that to get all the conditions for identification, to understand why there was a negative result, a failure of identification in the original paper, and how if you sort of then stated the formal conditions for identification, that's a special case. And so identification may hold, it may not hold. That's exactly what you know from simultaneous equations analysis that you learned. Depending on the prior information you brought to the input system, the system is or is not identified. And that's why you do things, you do it equation by equation, simultaneous equations, don't you? This equation is identified if the number of included endogenous variables is less than the number of less than or equal to the number of excluded exogenous variables, so on and so forth. That's why you go through rank. You go through the order conditions that way. All of that was prior information. What I want to do now is think about alternative structures. The first one is I'm going to call a partial linear and means model. The phrase partial linear model refers to environments in which we have aspects of the model are linear, but it's only partial, so some aspects are not linear. So what I put on the table, in other words, is to consider this variation of the environment we've been studying. I initially said, well, let's start off with a model in which omega depends on linear and everything. I preserve linear dependence on x and y, but what if there's a nonlinear dependence on m? Okay, that's a nonlinear means model. It's very similar to the linear means model. The only difference is it's some transformation of the expected value that matters. Everybody with me? I could have written down any I could be thinking about any parametric nonlinear system. I'm going to focus on this one because it's expositionally simple. Everybody with me on that? And so that's my question. Suppose I know mu. I'll make life simple. We actually know the nature of the nonlinearity. And that's really how to think about parametric nonlinear simultaneous equation systems. We think of it as we know the functional forms, but there's a finite set of parameters that we don't know. We ask, can I identify the finite set of parameters given that we know the nonlinear environment that we're working in? This is a special case of a nonlinear simultaneous equations model. In the linear system, at y equals x bar, we know that identification fails. My question to you is, in this model, if y equals x bar, does identification still fail? You've got to figure that out. And so we're going to figure out the following way. I should have written this on a slide. So the model, it looks like this. And so m minus mu m, mu jm must equal k plus x plus dy. So here's the nonlinear model I'm working with. Take the expected value of both sides and pull this thing over. Everybody with me? Let's assume that 1 minus j mu is invertible. I'm going to call this psi. In other words, I have a function. I'll call it z. 1 minus mu z is invertible, and I'm going to call the function psi. What that means is that psi inverse k plus cx bar equals m. Okay, I did a sloppy job here, I apologize. What I'm saying is you take the nonlinear model, take the expected value of both sides, assume invertibility of the nonlinearity, I get a statement that says this is m. How do we think about identification? Identification holds if x, y, and m are linearly independent. Is m linearly dependent on x and y in this model? No. It's non-linearly dependent. That's the whole point. And that is, we went to, remember the condition was I needed to say that x, y, and m were linearly dependent. That was the condition for identification. In this model, once I introduce a nonlinearity, they're always linearly independent. They're not functionally independent, they are linearly independent. And so the upshot is, for every nonlinear and means model, identification holds even if y equals x bar. The reason for that is that the failure of identification had to do with linear dependence. And once you introduce linear nonlinearities, that ensures linear dependence. Okay, I'm sorry that I did a sloppy job of explaining that, but all I want you to do is you solve for this, and you can show this nonlinearly depends on the other stuff, and you're done. That result, by the way, is much more general. There was a paper by Douglas McManus that appeared in the Journal of Econometrics in 1992. I think it does not get enough attention. And what it showed was that generically, nonlinear simultaneous equation systems are identified. And so what I want on the table is you take the linear and means model, you take the conditions under which identification fails, the nonlinear analogs to it, it always holds. And that tells us something important, and that is that the assumption of linearity is very significant in assessment of identification. All right, are there any questions on that? So, one message that I want on the table is that when we move from linear to nonlinear worlds, this so-called reflection problem disappears. In other words, the reflection problem is the specific problem of the failure of identification in linear simultaneous equation systems, and one of the paths for it to disappear is to work in nonlinear environments. To pursue that, discrete choice models of social interactions, they are generically identified. The reason for that is that the conditional probabilities of choices outside of non-generic cases are nonlinear functions of the x's and the y's. And so again, that's an affirmative message I want on the table. All right. Second question. What happens in dynamic environments? If you think about the literature on social interaction, the econometric literature, is this linear equation identified, or this linear system identified? The models are almost always atemporal. In other words, the question is, you depend on her, she depends on you. You depend on the average of everybody today, and you work out cross-sectionally the identification conditions. A different model would be one in which there are dynamic relationships between the variables. So one example would be that perhaps my beliefs at time t-1 affect my behaviors today. Okay, that's a model with sort of adaptive expectations. So I think I had some belief about what people are going to be doing in the summer of 1975, and that affected what I ended up doing in 1976. And that was my clothing example. Everyone sees that equation looks almost exactly the same as the linear social interactions model I started with, but with one little tiny difference, and that is that the timing of the expectations is not the same as the other variables. Everybody with me on that? Here would be a different type of equation. Would be this. Equation 13. I think about individuals who make choices, and their choices depend on their characteristics today, the context of their functioning today, and their beliefs about how things are going to be in the future. So I make my purchase decisions for clothing today based on what I think people will be wearing 6 months from now. So, and the serious point is, okay, clothing's a cute example, but the serious point is that when we think about people behaving in temporal contexts, intrinsic in those is we think about, we have beliefs not just about what happens today, but what happens at different points in time. So to make this a more serious one, I make choices today in educational effort based on what I believe will be the educational attainment of people in the future. If I expect to be in a world 2 years from now where everybody's graduated from high school, I make different choices today. If I expect to be in a world in which the labor market's filled with college graduates, I make different choices today. Quite generally, when we write down dynamic models of decision making, in which I have, think about the payoffs across, across time, that introduces the formation of beliefs over different time horizons. So, focusing on this equation 13, does everyone see that that is almost exactly the same model that I've analyzed already? Had there been no notion of time, I've already given you the conditions for identification. They come down to the change in the dimension of the space when I go from the linear combinations of x and y to linear combinations of x, y, and m. My question is, in this model, what happens with identification? Comment number 1. the logic of rational expectations still applies. I can always form mgt plus 1. What I would do is I would take the realized omega bar gt plus 1, I project on the information available. That would give me the expected value. That's what I call the instrumental variables approach to expectations formations, which is all that expectations formations is in linear environments. Okay? Now, it turns out I can solve explicitly for the expectations in this model. That's the Hansen-Sargent formula for rational expectations. And so the idea, in other words, would be the following, and that is the expected value of choices at time t, because it depends on the expected value of choices in the future, ends up with a complicated recursion. In other words, the expected value of the behaviors in the population depend on my beliefs about the trajectories of the x's and the y's. Okay, that's the logic of rational expectations in these forward-looking environments. The behaviors today depend on what I think the average is going to be tomorrow, but that means the average tomorrow is going to depend on what I think the average is going to be 2 periods from now, which depends on the average 3 periods from now, so on and so forth. And so what the Hansen-Sargent formula does is it just gives us a nice, clean way of understanding the dynamics of the paths of the x's and the y's and how they affect the expected values of the variables m. Everybody with me? So, let's think about equation 13. The identification problem abstractly is always the same. Are, in this case, x, y, xt, yt, and mt plus 1, are they linearly independent or not? Right? If they are, then identification holds. If they're not, identification fails. But notice that mt plus 1 is a function of my expected values for the x's and the y's all the way into the future. They depend more on more than xit and ygt. They depend on the entire histories of those variables because the entire histories determine my beliefs about their future values. Everybody with me on that? Therefore, and this is something Larry and I worked out a few years ago, generically these models are all identified. In other words, when we write down dynamic models of social interactions in which the timing for the belief formation is different than the timing of variables that affect me directly, implicit in that will be that there's linear independence of the different variables that affect me. And that will be true even if x bar equals y. The intuition is that the m that affects me is not determined just by x bar. It's determined by the history of x, but my beliefs about the evolution of the x bars. And so we see that there's a robustness to identification when we move from cross-sectional environments to intertemporal environments. And the reason for that, put differently, is in intertemporal environments, all of these instruments are generated for omega bar that don't appear in the initial equation. So the logic of rational expectations in dynamic environments generates instruments that facilitate identification. So this result is exactly the same type of result that gave identification in all of the classical linear rational expectations models, Hansen, Sargent, and the list goes on. So does that idea make sense? Remember, at the end, we're trying to ask, can I distinguish between how the expectational variable, the contextual variable, and the individual variables have distinct effects on me. I need them to be linearly independent. What the dynamic logic does is it breaks the potential for linear dependence, which occurred in the atemporal context. And so that's a second what I'm going to call constructive vision of the identification problem. Nonlinearity, if we can model it, is our friend because it facilitates identification. intertemporal relationships facilitate identification, because they're both roots to breaking the linear dependence, which was the guts of the reflection problem. Any questions on that? So what I want to do then is end this section of the discussion with a third variation of the baseline linear model. And this is what I'm going to put on the table as a so-called hierarchical model. So in the first lecture, I said to you that I thought that the social interactions literature was a good faith effort to understand, to introduce sociology and economics. What I want to also say is, sociologists, what a shock. They try to estimate social interactions too. It wasn't our idea to estimate social effects. And what's interesting is, in the sociology literature, a different set of linear models has been used from the linear models economists use. And they're called hierarchical models, and they come from a different logic. Different intuitive, implicit logic is the relationship between individual outcomes, individual characteristics, and social structure. So if you think about the linear social interactions model, you think it's additive. It says your behavior depends on stuff that's specific to you, plus stuff that's specific to your social structure, the social group that you function in. It's not clear why things should be additive. In fact, that's clearly an arbitrary assumption. That's not motivated by economic theory. When Larry, Raji, Jairam, and Brock and I wrote down our very rigorous formulations of the quadratic games to generate linear social interactions models, they assumed the additive separability of the different variables. That wasn't the theory. The theory is a conditional and an assumption. This is how you can justify the models in the literature. Sociologists have a different way of formulating preferences implicitly and different ways to formulate their statistical models. So this is how a sociologist, or if there's any sociologists here, then they can complain, but this is how we would translate the way that sociologists model social interactions into our econometric language. A sociologist would say the following, and that is, there's a relationship. Remember, we're living in a linear world. I was going to say I'm a linear girl, but I'm trying to reformulate the Madonna song. It's not going to work in real time. But anyways, the social interactions approach in sociology would say that if I look at people in a community, in a group called G, there's a relationship that's linear between an individual's characteristics, an individual's unobserved heterogeneity, and their outcome. But what the sociologists would say is the relationship between individual characteristics and individual outcomes is mediated by the social context. And the way that they formulate that is to say that the coefficients within a group that map individual characteristics to individual outcomes, they vary across the groups. And so in the hierarchical linear model approach, you would say that that constant K depends on both the characteristics of the group Y and the expected value of behaviors in the group M. And similarly, the coefficients that map individual characteristics to outcomes depend on the context, contextual variables Y and the endogenous variable M. Do you see the logic is different? It's one thing to say things are additive. It's the stuff about your family that affects you plus the stuff about your neighborhood. A different way to think about it is your neighborhood is the background variable against which there's a relationship between your family and you. And then in order to have purchase for empirical work, I have to place some structure on the way that the neighborhood, the environment, mediates the individual characteristic, individual outcome relationship. And this is simply a way algebraically to do that. Now this looks a little bit cumbersome because I have this matrix psi here and then a vector little psi. The reason for that is that there's a vector of coefficients here, but there's just a scalar that's added. Now, so before I go on, does everyone see that there's a different logic here to thinking about the relationship between the empirical relationship that maps group characteristics, individual characteristics, to individual outcomes? And notice that there's no sense in which the way that in applied econometrics, the social interactions models are structured. There's no, you can't really credibly say one is better than the other. If anything, this is probably theoretically more appealing. So what about econometrics? Well, the way to think about that is that I take this system and I can substitute in equations 17 and 16 into 15. And what that gives me is equation 18. So in other words, the hierarchical linear model approach to social interactions would say my behavior depends on, okay, the stuff we had before, the constant term, CXI, DYJ, JMG. That was the economist model, right? But in fact, I get additional terms here. This is the cross product with the matrix of the characteristics of the neighborhood and the individual's characteristics, and the expected value behavior of the neighborhood with the individual characteristics. So in other words, hierarchical linear models of the type that are introduced in sociology, what they do is they introduce a parametric form of nonlinearity. And it's kind of a simple parametric form. It just takes cross products of all the variables. Okay. And so that's a hint that maybe identification holds in hierarchical models even when it fails in the original social interactions models. So put differently, if these terms weren't here, identification would fail if yg equaled x bar. That's the reflection problem. But if yg equals x bar in a hierarchical world, there are other terms there, and hence we have to do a distinct analysis. So doing that distinct analysis, basically the question is always the same. Are the variables linearly independent or not? So solve for the expected value of behavior in a neighborhood, and what you will see is you have a complicated expression. And so if you assume yg equals x bar, this is the relationship between the contextual effects in a neighborhood and the expected value of behavior in a neighborhood. And that is a non-linear relationship. Notice M is functionally dependent on Y. It is not linearly independent. What is the upshot? Identification holds in hierarchical linear models. There is no reflection problem. The intuitions for that we did in the first context, which is when I move from linear to nonlinear worlds, the linear dependence condition that can't hold because the world is nonlinear. Or put differently, linear independence holds even though functional dependence, even in the presence of functional dependence. And so the message that I want on the table is that if you think about the sociological approach to social interactions, and again, this is a paper actually Larry and I wrote, oh God, we're old, 10 years ago. It turns out that all the sociological models are identified and sort of the problems that economists obsessed about simply don't exist in that world. Summary. The summary is that we took the baseline social interactions model. The appropriate way to think about it is to think of it as a type of simultaneous equation system that gives a very precise set of conditions for identification that derive from exclusion restrictions. Exactly the things you use from basic econometrics. And so identification will be contingent on the ability to bring credible prior information to the environment. That was the first set of results I wanted on the table. Then I wanted to look at three variations of the model. The first was the nonlinear and means model, and then we got the generic result that said that nonlinear parametric social interactions models will be identified. And the reason for that was this wedge between linear independence and functional independence. The second idea was temporal, and that is that when I have formed beliefs over different horizons about behaviors and they affect me, what that implicitly does is mean that the instrumental variables that are available to me for the endogenous variables are the entire trajectories of the x's and the y's. and that provides identification which didn't occur in the atemporal context. The third thing I wanted to put on the table was that there's another way to think about social interactions that is hierarchical in nature, and what that does is it produces different models. They actually have implicit in them certain types of nonlinearity, and as a result, those models are all identified. So the message, in other words, for identification in these environments is going to be that the classical failure of identification is going to, in parametric context, is specific to atemporal linear models. And so for that reason, if you ask Larry and me, do we think the reflection problem is an impediment to empirical work in social interactions, we would both say no. In other words, they're very special cases. And if you look at the universe of candidate social interactions models, when I say they're non-generic, they're a lower dimension set of the set of models.
So why don't we use these models instead of social interactions while they have the same, very similar theoretical interpretations? For example, this hierarchical models, they have very, they convey the same message of, very similar message to social interaction models.
Well, I think actually, so I'm going to say that a little differently, which I think we should consider.
Okay.
In other words, there are many dichotomies, there are many divisions in econometrics and empirical work. You do things parametrically, non-parametrically. What are the object? Do you do structural work, astructural work, so on and so forth. The social interactions literature is almost exclusively parametric. And so conditional on that, I wanted to say that the parametric models that have been the focus of the identification analyses are unusual in the sense that they are the knife-edge cases. And that in fact, in this universe of parametric social interactions models, identification is the rule, not the exception. Now, it's, an answer to any statement of that form is if you are convinced that the model that's not identified is the model one should use, then who cares if the others are identified, right? So implicit in this discussion is we don't have strong theory to say that it's hierarchical versus additive. We don't have strong theory on the timing of expectation about behaviors of others. We don't have strong theory that just says that it should be linear versus nonlinear. And so for those reasons, in our judgment, the focus in the literature has actually been off base because it's been focused on non-generic cases. In our view, I'll speak for myself, but I think I'll speak for my co-author too. We think that the action should be in asking questions of the form, what can you identify when you don't have strong parametric information, and what can you identify when you don't have strong social interactions information? All right, agree with me? So, that's, where's Dimitri? Well, if he's not here, I'm going to keep going. Sorry. I'm not sure when I'm supposed to take that break, so I'm just going to keep going. Okay, I want to go a little bit more. What I want you to see is what I put on the table was here was what I kept referring to the case where we made what's conventionally regarded as the desirable assumption about unobserved heterogeneity, which is it's orthogonal to the other sources of heterogeneity, the observable sources of heterogeneity. If you remember the first lecture, I claimed that there were three things to think about in identification. One of them was the classical simultaneity issue, which I've discussed. The second was what to do about correlated effects. And the third was what to do about endogeneity of social structure. The first comment to make is that with reference to analyzing these linear models, the question isn't, is there correlated structure, or does there exist endogeneity to social structure, self-selection? The question is whether those affect inference, or they affect what we can learn from the data. Put differently, we ask questions about correlated group effects, correlated unobserved heterogeneity, about self-selection, specifically because they change the error assumption of conditional expectations being zero. So the only sense in which we ask the question is assume that the conditional expectation of epsilon given x and y is no longer zero. What happens? And the answer to that question, and what can we do about it, the answers are going to depend on the reason why the conditional expectation is no longer 0. So to just give an example, and so that's why I want to divide the discussion now into 2 pieces. So what I could do is I could start off with a model of the form that said that, I have my linear social interactions model, and when I say to you that I'm going to introduce group-level heterogeneity, the easiest way to do that is actually have a group fixed effect. That's what I gave an example intuitively. I said if I have children in classrooms, one of the unobserved variables is teacher quality. And we'll think of teacher quality as a common shock to each of the students. And so that means that in addition to epsilon, I have another term, alpha g. Of course, I can solve for the expected value behavior in the group. It will depend on alpha g just as it depends on x bar, y bar, so on and so forth. Okay. So in other words, introducing group effects, that's the simplest way to induce correlation of the epsilon, of the unobserved heterogeneity, just means it means the expected values are going to change. Now, if you think about this for a second, you can see immediately why identification will fail or can fail if there are unobserved group effects. Unless alpha is assumed to be orthogonal to y and x bar and x, then I can't identify anything without additional assumptions. Because for any set of parameters that explain the data, I will give you a different set of parameters and a different choice of alpha that gives exactly the same probability descriptions for the data. Everyone see that? So in other words, you tell me that, here's the way I would do it. You tell me that dy, you tell me d equals 17, okay? It's identified. Well, I tell you, no, alpha g equals 17 times yg. Could I distinguish those? Of course not. So anything you call a social effect, I'm going to, just by definition, say it is equal to the unobserved group effect. Okay. That's the one-line proof, even though it's verbal, it's completely rigorous, that in these models, if we treat the alphas as fixed effects, if they're random effects, then that's okay, because they're orthogonal to everything. If they're fixed effects, identification fails. So, that's an example why correlatedness of the unobserved heterogeneity can be an impediment to identification. Because if I say that there's a social influence on individuals, I can't tell if it's a social influence versus just a common shock. Now, there's really 2 ways to think about dealing with that. So what would I do if there's these alpha g's in the system? Everybody with me? That's my question. What do I do about alpha g's? One way to deal with the alpha g's is to say that would be if I have panel data. If I have panel data, what would I do? I would difference them out. The alternative would be to use instrumental variables. So before I go on, is everybody clear? I'd say to you, I've relaxed the assumption these epsilon i's are uncorrelated with the x's and the y's. I've introduced something called alpha. That's another part of the error. It can be correlated with the x's and the y's. And I gave you a reason why it has to be correlated with the m's, because the expected value of m depends on the value of alpha. And so one approach we might take is to difference them out, and that's what a panel would do. So you know the standard techniques for differencing in panels. You can do it with discrete choice data, with discrete data as well as nice continuous linear data. And but that's a purely statistical solution, isn't it? There's no economics there. There's an observation that if you have panel data, you can transform the data. You can basically permute it in such a way to eliminate the fixed effects. The second approach is to try to find instrumental variables. And that's one of the ways to understand the search for instrumental variables. So if I say to you, I want to understand the effect of peers on each other in a classroom, and I think that there's teacher quality heterogeneity, I would look for an instrument that moves the behavior of the students that is uncorrelated with teacher quality. Everybody with me? Okay, and so again, just to give you an intuition as to why instrumental variables appear in these models. I want to say just one thing about instrumental variables in this context, is they're extremely hard to justify. And the reason for that is, and this is why I emphasize that these types of problems of correlated heterogeneity and correlated shocks, they're statistical problems. That means we don't have any behavioral theory about them. To just say there's teachers there doesn't explain anything about why teacher quality is of a certain type in a classroom, etc. The difficulty in using instrumental variables here is if I don't have a theory about the alphas, it's hard to see. It is often difficult to come up with an instrument where for the unknown alpha, I know it's uncorrelated with the alpha. That's the trick, essentially, in an instrument, isn't it? I need something that's correlated with M, but not correlated with alpha. That's the instrument I'm looking for, right? And the problem I have is, since I have no theory about the alpha, how could I really plausibly do that? That's comment one. Comment two is to notice that instrumental variables come in two flavors. When I talked about rational expectations, I implicitly talked about instrumental variables, didn't I? When I wrote down my baseline social interactions model, what were my instruments? They were the X bars. I said if I have an X bar that didn't already appear in the equation, that identified the social interactions. That's an instrument. There was an exclusion restriction that said it didn't appear in the equation to begin with. And X bar, by the logic of the model, is useful to me. That same principle appears throughout the rational expectations literature. When we write down rational expectations models, you think about Euler equations, dynamic models with the expected value of something as a function of other things. Those models implicitly give us instruments. Why? Because if I tell you this thing equals the expected value of something else, then the realization of that something else minus its expected value is a forecast error. It has to be uncorrelated with the things that I forecast, the information I have. So the philosophical point is the following, and that is that one source of instrumental variables is implicit in the models we write down. When I write down a simultaneous equations model with exclusion restrictions, that meant that the model had implicitly defined instruments. When I write down rational expectations models so that certain things are conditional expectations of other things, and therefore other things are forecast errors, that implicitly defines instruments. The other approach to doing instrumental variables is not to ask, does the internal logic of a model generate instruments? It's to ask whether or not we can be clever in identifying an instrument that's outside the model. In some cases, we can be clever. That's really what natural experiments are. There are cases where you identify an instrument that's not part of the logic of the model, but you can argue for a priori reasons. It moves one thing around without moving something else around. So if I say there's an earthquake, and it changed things, the earthquake's an instrument, because it meant this thing moved around the earth, so because the classroom moved around, it shook up and down, the walls broke, or what have you. But I can assume that it's not correlated with other things. And so the point is not to poo-poo instrumental variables or not. I just want you to think about the practice of empirical work. It is essential to recognize that many of the sources of instrumental variables are intuitive. They're outside the logic of the model, and the validity, the credibility of the assumptions can often be problematic because we don't take the models that, we don't believe the model would have particularly strong information of that form. Okay, so to give you an example I've written about many times, in the economic growth literature, geography is often used as an instrument for international trade. So the idea is to say, trade affects growth, but trade's endogenous. So here's an instrument, geography, whether a country is landlocked, or whether a country is big, or what the country's weather is like. But those are instruments for trade, and that can move around trade and give you a causal relationship to growth. My claim is that that's nonsense. and I'm being blunt, because there's no reason to believe that geography doesn't directly affect economic growth. In order to use the instrument, you have to exclude it from the model to begin with. And so there's nothing logical about the trade growth relationship that says geography is an instrument. Social interactions models have this same feature. And so the reason I wanted to finish this right before the break was to put on the table the following proposition. And that is, if we think about we have the classical identification problem, then we have the correlated heterogeneity identification problem. This is the one that's particularly hard because these models themselves have under-theorized correlated heterogeneity, and it becomes difficult to credibly identify instruments because those have to come from outside the model, and we don't have a theory of the correlated heterogeneity. Okay, so if you look at the Hamper chapter Larry and I wrote, we criticize instrumental variables ad nauseum. I'm sure our criticisms are correct, but the serious point, that's what I want on the table. So we're going to take the break now. I have to. And then when we get back, I want to talk about self-selection. All right, so what I think, the important principle of dynamic optimization is to adjust given information. I've been going slower than I expected, so I think what I will do is I will finish the discussion of self-selection, and then rather than talk about intergenerational mobility, I'm going to talk about a paper that Larry and I wrote that's kind of a very general treatment with Roger Sharma and Buzz Brock, a very general treatment of identification and social interactions. So that should exhaust the time. Okay, what I want to say about self-selection is the following. So as we have the classic identification problems, we have the issues of correlated heterogeneity, which I treat as a statistical problem, and I merely put on the table that it can often be problematic because the instrumental variables approaches would have to be outside the system as opposed to inside. But I want to finish with the self-selection. And self-selection is a ubiquitous problem in empirical work in economics and social science, and it's a natural thing to model in these contexts because if I'm talking about organizational groups, social structures called residential neighborhoods, or classrooms, or schools, or firms, in each case there's been some process by which people became members of it. And so there's an endogeneity to the social structures, to group memberships in these cases, that one would think have consequences. And I gave an example in the lecture yesterday of why that would be true. If I'm asking about the effect of high-quality schools on the children of immigrants, I need to account for the fact that children of immigrants who attend high-quality schools are going to have qualitatively different parents than those that did not. So, in thinking about this approach, really what I want to put on the table is the following. And that is, if we think about social interaction structure, a way to proceed is the following. Okay, everybody with me? And that is that I'm thinking about this cross-sectional regression of this individual's outcome depends on the group individual's characteristics, the group characteristics, and the group behaviors. And my concern is that what was going on in the environment is people chose to be members of these groups. Now these groups, of course, have constraints in the choices, and so the reason that poor people don't live in Beverly Hills is not because they don't desire to live in Beverly Hills, they can't afford to live in Beverly Hills. And so when you write down the decision problems, the choices, of course, are preferences, constraints, and belief structures themselves. But what I want to put on the table is the following idea. And that is, when I'm thinking about the endogeneity problem, here's a way to think about it. Everybody with me? And that is, when there's self-selection, the conditional value of the error, the unobserved heterogeneity, given all the observables, is no longer zero. Right? Now, by definition, if I take epsilon, and epsilon has a conditional expectation that's non-zero, I can divide epsilon into two pieces. The conditional expectation plus the thing that's left over. Call the thing that's left over xi. And by definition, what's the conditional expectation of xi? It's zero. So everybody gives us an identity. I can divide any unobserved heterogeneity into its conditional expectation, and then the residual, which has an expected value of zero. Okay? So if I think about the regression, in other words, my social interactions model, the problem of self-selection is that the error is no longer, the epsilon has a piece of a non-expected value. And from that vantage point, it at least gives a hint as to how I might want to deal with it. But before I go on, does everyone see that when I introduce self-selection, what I'm saying is, if I know the values of the x's, the y's, and the m's in each of the neighborhoods, the conditional value of an epsilon in a given neighborhood is no longer 0. And this very ungainly expression is the conditional value of the error. Okay. So, from this vantage point, you can see that the identification problem is very simple, and that is that part of the unobserved heterogeneity has a non-zero expectation. Now, what I want in the table, of course, is that there are different ways to think about how would I deal with an environment in which the conditional expectation of the errors is non-zero. I've already turned my nose up at one of them. I said, well, instrumental variables, yeah, if you have them, that's a wonderful thing. But you may not have them. They may be hard to justify. And so what I want to put on the table is another way to deal with self-selection, and that's the Heckman approach. And so to think about it, this is what I mean. If I said to you the expected value of the error is no longer zero, is not 0, it has some non-zero, suppose that I actually had this term. In other words, if I gave you the expected value of epsilon, you could use that and say, well, you know what, I'll stick that in the regression. It'll have a coefficient of 1. And if I added that regressor, then everything would be just fine, wouldn't it? Okay, so that's the background. Is, okay, you make the observation that if the error at the end of the heterogeneity has a non-zero expected value, if I gave you the non-zero expected value, then of course you just solve for it. You would subtract that off the omegas. We'd be back to the model that we've been discussing. So the profound insight, the stroke of genius in the Heckman approach was to say the following. It may be the case that we can estimate either the expected value of the error, given the observables, or we can estimate something that is proportional to the expected value of the error. Okay, that's the so-called control function approach, and that's the Heckman selection correction. Okay, so is this thing, people have seen control functions, selection corrections before? So the idea would be the following, okay, just so you understand. And that is and you notice that the logic is going to be very, very straightforward here. So the idea would be that I say to you that people have made choices, they're members of one of G groups. Okay. By definition, why are you a member of this group versus that group? Because you get a higher net utility from this group versus that group. Remember, net utility includes the price of living in the neighborhood. So the idea is, in other words, to say that each neighborhood has for each individual, there's an I star IG. That's the quality I assign to neighborhood G. That's not observable. But what you assume is, I, by definition, tautologically, my choice of a neighborhood is the neighborhood that maximizes my payoff. Right? So that's the underlying logic. If I want to somehow account for the fact the expected value of the epsilon is no longer 0, one way I can do that is explain why it's not 0. And the reason it's not 0 is because I chose to be in that group because it maximized my utility. And so the logic of the Heckman selection correction was to say the following: if I know that if you're in the private school or not, you're in the job training program or not, the reason you did it is the expected value of being in the job training program was higher than not being in it. Okay? Then what he was able to do was to show that he could compute the expected value of epsilon in the regression, given the fact you were in the job training program, or given the fact you were in the private school, so on and so forth. Put differently, the solution to self-selection was not to find an instrument outside the system. It was to write a richer model. It's what I refer to as model expansion. The logic of model expansion was to say, don't just say exogenously people are in groups, run a regression of the effects of the groups and the outcomes, but rather say that the observed groups for each individual were endogenously chosen, and I use that endogenous choice to determine what the expected value was for the epsilons. And so the so-called Heckman selection correction, which is now generalized to be called a control function, is you control for the self-selection by putting in an expression that is the expected value of the error. So in other words, you essentially estimate equation 26. Step one of the procedure is to come up with an estimate of the expected value of epsilon given the group. That derives from economic theory. Now, if I observe that you're in a certain group, that should tell me something about the expected value of your epsilon when it is associated with the fact that you're in one group versus another. Now, I should say that in the classic selection corrections, you can't actually estimate the expected value of the error. You estimate the expected value of the error up to a constant of proportionality. So what you end up with is an estimate of the error, the expected value of the error, up to a constant proportionality. You just put that in the regression as an additional regressor. Its coefficient is the inverse of the constant of proportionality. But I once again then have a standard regression. Because once I have controlled for the expected value of epsilon, the new unobserved heterogeneity xi has an expected value of 0. So in other words, from the vantage point of the selection correction approach, this is what is done. Okay? You first model the process of group membership. You use it using this approach that there's a latent value for each neighborhood, and my choice by definition is that which is maximal. I then, from that, I compute something that is proportional to the expected value of epsilon, and I add that as a regressor. Okay, that's the classic selection correction. Modern versions of selection corrections are non-parametric. They do them under weaker assumptions than the original 79 paper. I should say semi-parametric, so on and so forth. But they all have the same logic. So before I go on, I want to make sure everybody's comfortable with what the thought experiment is. Rather than have this deus ex machina of instrumental variables brought in, you expand the model to model the process of group membership. You do it in such a way that allows you to construct a proxy for the expected value of the epsilon for each individual, given the fact they're a member of a group. And so to play that out, if I was looking at immigrants that live in Palo Alto, California, versus immigrants that live in East Palo Alto, or say it was a poor community, there'd be a selection correction. The conditional value of the epsilon for a child whose parents put them in Palo Alto High School is different than it is for the children whose parents didn't do it. The way you do it is you assume that each parent maximized, and from that you infer what the expected value of the error had. I'm going to skip the algebra for that, because for our purposes, the only thing that matters is you can do this. And what I want to emphasize is it is unlike instrumental variables, which I call the cleverness approach. This approach is even more clever, because it said use economics, use economic theory, expand the model in a principled fashion to account for the endogeneity, in this case, of social structure. And so for our purposes, the control function approach to the endogeneity of social structure is nothing more than the application of the Heckman idea, which amounts to adding a regressor to the equation. Okay, that's it. Now, of course, there are ways to criticize the control function approach. Many control functions are parametrically constructed. You say, well, we don't like the bivariate normality assumptions of errors, and blah, 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 blah. And so we can have legitimate discussions about the role of assumptions and whether or not to use a parametric or a semi-parametric correction, and so on and so forth. But nevertheless, there's a philosophy here that I want you to see, which is in the presence of the endogeneity of social structure, rather than treat it as just saying this means we can't identify, model the endogeneity of the social structure, and that allows us to come up with a new regression whose new error properties are the same as the original model. I gave you the identification conditions when the errors are the unobserved heterogeneity, the errors are orthogonal to the regressors. Once you implement the Heckman selection correction, or whatever generalization is appropriate for the environment, You once again have a model in which you have outcomes depend on individual level variables, group level variables, and unobserved heterogeneity that is orthogonal to the regressors. And so what I'm emphasizing here is that when I say to you that, and this is the point I wanted to really hammer home, correlated heterogeneities of the type I referred to as like teacher effects, those are really statistical problems. Self-selection is an economist problem. That says that we need to have a richer environment in which we're doing the analysis than just assume there was exogenous assignment of individuals to neighborhoods or to groups. All right, so that's all well and good. It's just a different route to solving the problem. But I want to push this a little bit harder. Before I go on, does everyone see that in the presence of self-selection, if I were to engage in a self-selection correction, what I do in essence is I add a regressor to the equation. So if there was no self-selection, that regressor wouldn't appear. That's our initial equation. And we have conditions for identification. In the presence of self-selection, we add a regressor. By the way, are we done, or is there something else we have to figure out? There's something else we have to figure out. That's a new equation. After all, I gave you the conditions for identification when the selection correction was 0. That was if the selection correction equals 0, that says these are the regressors that we're going to work with. When I need a selection correction, it's actually a different set of regressors. Now remind me, didn't identification depend on the relationships between the regressors in an equation? Well, if that's true, then it must be the case I have to redo the identification analysis. Because after all, I can't simply say what was true when there was no self-selection is true for the new equation because I have a new regressor in it. And so the observation now is if we model self-selection, we can construct a new regression for social interactions, one that accounts for the self-selection. But we then have to do the identification analysis in the context of the new equation. Okay. So, by the way, is everyone with me? So in other words, I've said, I have a model. If there is no self-selection, I know how to do identification. If there's self-selection, I have a new regressor. And now I have to redo the identification. What is this regressor? Well, I told you, the regressor is by definition the selection correction. Is the selection correction a group level variable or an individual level variable? It is an individual level variable. My selection correction differs from your selection correction. If you live in Beverly Hills and your parents have $100 million and my parents have $5,000, we get different selection corrections. Does everyone see that? That's the whole point. So in other words, when you construct selection corrections, they're actually individual level variables, aren't they? So when I went to an environment with no selection to an environment with selection, what have I introduced? A new individual level variable. Did everyone see that? Because the selection corrections are individual specific. They're the expected value of my error given everything. It's the expected value of your error given everything. And as long as we differ on our x's, we get different expected values. Okay, that sounds good. What was the condition for identification in the linear needs model? What was the necessary condition? I needed one x whose average was not in the y's. Right? That was the necessary condition for identification. One individual level variable whose group level average was excluded from the original model. My question to you is, in this model, where's the average of the selection corrections? It's not there. And it is not there because I made it up that it's not there. It's not there as a matter of theory. And so I have cashed in the check. I promised you I would give you an example of an individual level variable whose group level analog, everyone with me, is omitted from the equation as a matter of theory. And this is the example. So now consider the following. Suppose that y equals x bar. Everybody with me? That was the bad case. If y equals x bar, in the absence of self-selection, is the model identified? No. That was the case I went through. That was the reflection problem. Suppose that y equals x bar, and there is self-selection. Is the model identified? Yes. Because the selection corrections are an individual level x whose group level average does not appear in the model as a matter of theory. And so lo and behold, self-selection could take it. If I had an environment with a random assignment to neighborhoods, identification can fail. But if there is self-selection into the neighborhoods, identification holds. And it's self-selection on unobservables. Okay, so in other words, if we work through the logic of the selection correction, we see it's really nothing more than an individual level x. And it turns out that in this context, that individual level x bar is not part of the equation. Hence, the presence of self-selection could facilitate identification. Now that should sound strange. I've just told, don't you hear things? You say, oh, random assignment, random controlled, randomized controlled experiments. Those are the gold standard for empirical work. Don't we read that all the time? Well, I do. I don't believe it, but I read it all the time. I just gave you an example where if there were a random assignment of individuals across groups, identification would fail. If there was endogenous choice of group membership, identification holds. That sounds like the opposite of saying randomized assignment is the best thing. So now we have to think about that. First of all, everyone see there's something to think about. In other words, the usual way we think about identification is that it would be good if I could randomly assign people to different treatments or what have you, because I could see what the effect is of the neighborhood. I randomly assign one person to the high-quality neighborhood, somebody else to the low-quality neighborhood, and I see what the difference is. Right? Isn't that the sort of story we tell?
Gold standard.
Yeah, that's the gold standard. But I've just given you an example, and it is mathematically correct, so the example is right. Okay, but I didn't make a mistake. This is true. Okay. In which the gold standard failed. It's tarnished. It turned out to be fool's gold because it was the environment with self-selection, non-random assignment where identification held. And we have to figure out why. Let's think about this. Okay, before you see, this is actually an important point. In other words, I've written down an environment in which non-random assignment was helpful for identification. That sounds strange. Here's the way to think about it. The answer is I changed the game. In a world with random assignment, there is only one behavior. It's the behavior of what happens after you are randomly assigned. Encoded in those behaviors is information about social interactions. In a world in which people choose their neighborhoods, there are two behaviors. There's the behavior that occurs once you've chosen, but there's a second behavior, which is the choice of the group. There is distinct information about social interactions in the choice of group. And so by expanding the model, I actually change the information we had. I get to observe two behaviors by each person, and I can use those to triangulate the presence of social interactions. That's the reason the identification reemerged. In other words, what I achieved in addition, in the case in which I had self-selection of the neighborhoods, it benefited me because I get to observe another dimension along which people behave. And that helps me pin down the presence of the social interactions.
Now for you, I want it to be, first of all, to say, here's an example where the gold standard was tarnished, it didn't work. But I want you to see why it didn't work. It's because the gold standard of random assignment rules out the information, rules out using choices of the assignments as a source of information. In this context, there is information in those choices, and that helps pin down the social interactions. So to play that out, everybody with me on that? So you see, that's a different way to think about what random assignment does and what it doesn't do. In this environment, random assignment delimited the information that is available to us because we can't observe how different people make choices. So to play this out, if you observe the poor family in the rich neighborhood, in the high-income neighborhood, there's information about social interactions. Or actually, there's information about school quality. There's a reason they decided to spend 70% of their income to live in Palo Alto. It's because the schools have an effect on their kids. And so the fact that I observe immigrants who are spending all of that money to live in these horrible apartments in Palo Alto and have access to the schools, that should tell me something about the value of the schools. So if there's purely random assignment, I lose that information. So that's the message I want to leave you with in thinking about the endogeneity of social structure. The message is endogeneity of social structure can facilitate identification because it represents a distinct behavior, and that distinct behavior encodes information about social interactions. Please.
Isn't this overestimate the quality of the school in Palo Alto? In a sense, if a kid is from this kind of family where the education is valued, and even if they go to the lower quality school, they might become stars. But like in Palo Alto, they're still stars.
It's a fair comment, but notice the structure of the model. The effect of Palo Alto schools is D. It's additive here. Okay? I want to identify D. What the selection correction does is it says that the poor kid in Palo Alto has a really high expected value of epsilon. I counted for that, so I will still identify D. What would happen is if I didn't put in that epsilon, that estimate of epsilon's expected value, then I get an overestimate. Because the kids who are poor that are in Palo Alto have really high epsilons. Once I put that in, that controls for the problem you're worried about. All I cared about was the identification fails. So there's two types of identification failure. One is I don't account for the self-selection and I get the wrong answers. The different failure of identification is the correlatedness of the different regressors in the model. The first failure of identification I control for by the selection correction. The point is there's a bonus to that. By controlling for the correlatedness of the errors in the observables, I get the bonus that I can disentangle the presence, the effects of context versus endogenous social structure. And that's the paradox, and the reason is I have an additional behavior I get to look at. So that's a message I want to take. Now, the preaching message, the proselytizing message, is that I think it is extremely unhealthy to these ideas, randomized control trials. Those are bad ways to think. And I mean that seriously. A good way to think is to say that there are questions we wish to answer, and the way that what we care about is what are the approaches that will most successfully answer them. In some contexts, randomized controlled trials are the gold standard. Okay, there are certain types of drug trials where that's exactly what you want to do, because what you want to know at the end is the effect of the drug. In other contexts, we wish to know different things. I wish to know something about the utility functions of individuals, in other words, or I want to know something about the effect of neighborhood quality on outcomes, because of the effect it has on either preferences or constraints or beliefs. It's not clear. That's not the same thing as wanting to know the effect of a drug. It's wanting to know something about a mechanism. And the revelation of certain mechanisms may require, we would think about, may have different data requirements. Okay, so my point is not that randomized controlled trials are unhelpful. Of course they're helpful. It'd be a crazy thing to say otherwise. What I'm objecting to is the idea that there's a hierarchy of sources of information that is independent of the questions we wish to answer. And the reason I harp on this example is that if my question is to understand the determinants of individual outcomes, individual versus endogenous versus contextual social effects, the sorts of behaviors that will reveal that, it may be that violation of so-called random assignment is facilitating for identification. Random assignment is good for answering certain questions, not good for answering other questions. To give you a silly example, if I want to know why people choose neighborhoods, randomly assigning them to neighborhoods will not tell me. Okay? So if that's my objective, by definition, it's the wrong thing to do. This is more subtle. My objective is to understand the value of neighborhoods and the effects of neighborhoods on people. And so it is useful to me to see what happens when people have the option of choosing them. So there was an additional behavior that I used for the triangulation. And so I think that there is even the point is not to say don't use random assignment, don't, there aren't, or that there are no contexts where that clearly is exactly the ideal data set, but rather to avoid reifying a methodology or a type of data is somehow superior to other data independent of the questions you wish to answer. Okay, my view of empirical work is one should be extremely undogmatic about methods and tools. Our job is to answer questions. We should use whatever tools best answer the questions, not sort of have a philosophical preference for one versus the other. Let me add in that context that it is also important to recognize that if one focuses on a certain methodology and says that's the way one has to do things, it by definition will rule out certain questions. And so if I said to you, I wish to write a paper on the causes of the First World War, that is a perfectly scientifically valid question. There is not a random assignment solution to answer that. Right? Unless somebody figures out the quantum mechanics of multiple universes. The serious point is that methodologies have to be assessed relative to the questions they can answer. And the reason I spend time on this is that it looks superficially paradox. It looks like a paradox. The non-random assignment of people to neighborhoods revealed neighborhood effects. If they were randomly assigned, you can't see the neighborhood effect. The answer is there's no paradox because there's a new behavior, and that behavior encodes information. And so at least I would take it as a philosophical matter to all empirical work. You choose the tools and the approaches based on the question you want to answer. Okay. So I think that's all I want to say. Actually, let me readjust. Okay. What I'm going to do is spend a little bit of time. I'm going to move away from discrete choice models to binary choice models. Yeah, I apologize that I'm engaged in this re-optimization every 15 minutes in the lecture. I think what would be most efficacious is if I complete the discussion now of linear models and talk about discrete choice models. So, what I want to do is to write down a discrete choice model of social interactions. And so this is something that I've worked on, as Broadberry worked on variants of this. And the way I want to think about that is to say, I want to basically ask the identification questions for this environment. So the idea is going to be that people make, now it's not a linear model anymore, it's a discrete choice model. And so the idea is that there's a payoff to each of the choices. I'm going to code the choices -1 and 1. Okay, my payoff depends on my choice. A constant term multiplied by my choice. There's CXJ multiplied by my choice, dy multiplied by my choice, JMG my choice, and plus an error. And the difference in the errors is assumed to be extreme value distributed. Okay. This is the canonical logit model of this binary choice. Notice it is the analog to the linear means model. If I make a choice, there's an effect CXY on my utility, there's an effect dy on my utility, and there's an effect JM on my utility. So it's just mapping the linear model into the discrete choice language. Any questions on that? But it's a different environment. It asks you to go to school or not go to school, graduate from high school or don't graduate. you attend college or don't attend, but it says as a payoff if you attend college, as a payoff if you don't attend college. You compare the two, you got to choose one.
Excuse me.
Yes.
What's the term epsilon I? What's the term epsilon I?
Epsilon I is the unobserved payoff to each of the choices. There are one unobserved
And what is
heterogeneity.
its expected value?
I know my epsilons. Oh, I'm sorry. So I'm the actor. Okay. The thing I don't know about is what other people are going to do. I know my x's, I know the y's for my group, and I know my idiosyncratic payoff. That's the behavioral problem. It was a good question, thank you. For the econometrician, I don't know the epsilons. What I assume as the econometrician is I know the density of the epsilons. That's the Logit assumption. Okay? And so all this is doing is, again, respecting that there's aspects of individuals I, as the modeler, can't see. So, if I say to you, what is the probability that I choose 1? That's the probability that my payoff at 1 is higher than my probability at -1. Okay, there's a typo there. And so that probability will be exponentiation of k plus cx plus dy plus j divided by ex, that stuff. The second term, multiply everything by -1. I'm sorry about that. There's a big typo. So in other words, it should be ex minus k minus cx minus dy minus j. Okay, that's those are the Logit probabilities of choosing 1 versus -1. Everybody with me? And so the expected value of the choice in a group is going to equal the hyperbolic tangent k cxi dyj plus m. And that's the hyperbolic tangent function. All right. That's the environment. So notice all I did was I said if you're going to do social interactions analysis with binary choices, what you do is you write down a payoff if you make choice 1, which is a payoff for the group. It depends on the group characteristics and the endogenous characteristics of choices. And there's a choice for -1. By definition, you choose the one that has higher utility. And so what do you do as the modeler? As I figure out what values of k, c, d, and j maximize the probabilities of the observed choices. And that's all you do in binary choice. Same thing is for multinomial choice. Am I going too fast and making clear what the thought experiment is? I have a population of individuals. You chose 1, you chose -1, you chose -1, you chose 1, so on and so forth. There's a likelihood for those choices. Those likelihoods are going to be the conditional probabilities of the choices multiplied together. The given conditional probability of a given choice has the Logit structure. And so what I do when I estimate the model is I maximize the probability of the observed set of ones, the zeros, and -1s and 1s I see, and that determines the values of the parameters. The only trick in the model is to recognize that the expected value of the choice in the group is going to be the average of the expected values for each of the individuals. The expected value for an individual is just the hyperbolic tangent of k plus cij plus dy plus j. So that's the model. These are the results that I want you to know. Number 1, in binary choice models with social interactions and in multinomial choice models with social interactions, these models are identified. Now the parameters are identified up to scale, and the way that you pin them down is you basically, I made an assumption that the errors were the probability of the error differences. The distribution function is 1/1 plus e to the minus xz. That normalized the density of the errors. Okay, so the result basically is that discrete choice models of social interactions are always identified. It doesn't matter whether the x's and the y's have a one-to-one mapping. The reason for that, please.
Just a clarification. So that you said before is that you can compare the coefficients between groups.
Yes.
The scale is the same.
Yes.
Okay.
So the idea is that The utility to me of graduating from high school is C times XI. That's true if I'm in Beverly Hills School District or if I'm in a different school district. And what distinguishes the Beverly Hills School District from the other school district is the Y's are different and the M's are different. So I'm sorry I'm going too fast on this, but what I want on the table is I can think about a discrete choice, which there's utility from making one choice versus another. And each person, and then the groups differ because they have different M's and Y's. I could write down exactly the analogy to the linear means model, in which the payoff to what choice in the neighborhood depends on X's, it depends on Y's, and it depends on M. The difference between the two is that the way I think about it is I have a probability of each of the choices for each person in the population, and the econometric exercise is to choose the parameters to maximize the probabilities of the observed choices. Make those the most likely things I see. And so the first result is the parameters of the discrete choice model, be it binary choice the way I formulated it, or the analogous multinomial model, those are identified. The reason for that is the following. The expected value of the choice. If I look at the choice in the neighborhood, the expected value of a choice in the neighborhood is simply the average of the individual expected values. So within a neighborhood, everybody faces the same M. Everybody faces the same Y's. We have different X's. So I just integrate across the X's in the neighborhood. Now notice that the expected value of the average is there and there. So, and there's no closed form solution to it, but that's fine. The point is that that's the definition of the expected value of the average in the neighborhood, and it is a nonlinear function of the X's and the Y's. And so for the same reasons that the nonlinear means model was identified, the discrete choice models are all identified. Because in discrete choice environments, the relationship between the expected value of the average choice and the X's and the Y's is nonlinear. Because probabilities under a Logit assumption and generically are nonlinear functions of the X's and the Y's. Right, so there's a difference between linear models and discrete choice models. There's a possibility for identification to fail in the linear environments. They will generically hold in the discrete choice environments. The intuition is exactly the same for the nonlinear simultaneous equations model. Second idea. If I don't know my calculations here, I assumed I knew the density of the errors. That's kind of standard, that's what it means. I say there's a Logit model. That means I assume the difference of the errors has a certain relationship. If you say you have a probit model, you assume a different relationship, distribution function to the errors, right? Here's a second result. This is basically is a minor variation of the argument of Mansky's. And that is, if I don't know the error density, I can identify the error density. So in other words, if I give you a discrete choice model of social interactions, I can identify K, C, D, J, and the distribution function for the difference of the errors. Now I want you to see why that's going to happen in this environment, because this is going to give you some powerful intuitions to what gives you identification. Suppose I just looked at one group of individuals. Everyone with me? What could I identify within a single group? Well, if I knew the density of the errors, I could identify C. How come? Because if I look within a group, everybody faces the same Y, everybody faces the same M, right? Those are like constant terms, but we have different X's. So the variation of the X's within a group will reveal what C is. Furthermore, this is the more subtle argument. If I look within a group and I see how the probabilities change for different values of X's, that will tell me what the density is of the errors. That's a much more subtle argument, but it can be made. So in other words, if I see that the probability, as I go from one x to another x, how much it changes. It tells me how much the errors variation has to be. So within a group, you can pin down the density of the errors as well as the values of the C's. That's idea number one. So one group is sufficient to identify those two facets of the model. In other words, within a group, everybody faces the same social structure, and so what I can pin down are the sources of individual heterogeneity. What do I learn when I move across groups? That reveals D and J. As I move across groups, there's different combinations of the value of Y and the value of M. And it's by looking at how the probabilities of choices are varying across groups as those things move that I can determine the parameters associated with the Y's and with the M's. Now, across groups, the impediment of identification would be if M and Y were linearly dependent, and I couldn't tell which one was driving things. However, that's the beauty of the system. If Y moves around enough, they can't be linearly dependent. That's what I mean when I say probabilities don't allow, if there's a big enough support for the Y's, Y and M cannot be linearly dependent. Because after all, M has to be between -1 and 1. It's bounded. That's the expected value of the average. And the support is -1, 1. If the Y's are moving around like this, you can't have a linear relationship to the bounded support. And so it is intrinsic to the logic of probabilities that we have identification of the D's and the J's. So those are the ideas I want on the table in understanding discrete choice identification. And they're germane in some sense to thinking about identification in any environment. If I look within a group, that's going to pin down the C's. It's looking across groups that's going to tell me what the D's and the J's are. And what I need for identification of the D's and J's, aren't linearly related. In the linear models world, the way they're not linearly dependent, was the presence of this X bar that was moving the M around and not the Y's. In the discrete choice world, we don't have to worry about that because probabilities are nonlinear relationships. Okay. And so that, there's a fair amount of algebra, tedious algebra, not hard algebra, but tedious, to prove all of that. But all the intuitions are very, it's very intuitive. So that's the first set of ideas for discrete choice models as distinct from linear models. In other words, what matters in the discrete choice environments is that their conditional probabilities have to be nonlinear. Hence, we can identify them. So far, it sounds like the understanding identification in linear models and discrete choice models is really pretty much the same thing. In other words, within group variation, X is what would reveal a C. Would reveal the C parameters. It's cross group variation in the Y's and the M's that would reveal the D's and the J's. And so then the question for identification is whether or not the Y's and the M's are linearly dependent. So in that sense, the arguments are mathematically the same. Here's where they're different. What about fixed effects? In other words, I could write down a discrete choice model, which is a fixed effect. It may be in this classroom there's a good teacher, so suppose the outcome is work hard or don't work hard, it's binary. This classroom has a good teacher, sorry. This classroom has a not so good teacher, so on and so forth, right? The way that I would express that is to say the expected value depends on the stuff before, but there's also a fixed effect. And so working hard, its payoff to me depends on the value of alpha G. And so, again, with no assumptions, identification is going to fail. The question is, can we make assumptions in a discrete choice case that are ones we might be able to live with? So that's really where I wanted to end the discussion. And so where we are is that we're in a binary choice world without fixed effects. Identification will hold. With fixed effects and no description of what the nature of the fixed effects, identification, of course, fails. Because what I would do is I would set alpha g equal, if you tell me this is what dy equals, I'll say, no, that's my alpha g. And so I have to rule those types of things out. What I want to end the discussion with is there something about discrete choice models that makes them qualitatively different from linear models that can help us with identification? So something Larry talked about in the theory lecture was the question of multiple equilibria. Linear models have unique equilibria. But discrete choice models may have multiple equilibria. This is the intuition. I kind of like that. It gives it, there's like some drama there. It's almost like. That's a 45-degree line. And I should make these multiples. Suppose everybody's identical. Okay, so this is just for clarity. Okay, we're playing some sort of game in which a bunch of identical actors make their choices. Okay, I can restrict myself to symmetric Nash equilibrium. If the best response function is upward sloping, that's complementary. It says that I do more when others are doing more. If the best response function is linear, how many times can it intersect the 45-degree line? The answer is only once, right? And so that's an equilibrium is the intersection of the best response function with the 45-degree line. I need everybody to make the same choice, right? In contrast, if this is the best response function, there's 3 equilibria. That one will not be stable, but there'll be 2. That's a nonlinear best response function. It turns out that discrete choice models with logit errors, they all have S-shaped best response functions. What determines whether or not the best response function looks like this or looks like this? So in other words, there's lots of S's I could draw. Some S's would intersect the 45-degree line 3 times. Some gently slope and only intersect 1 time. The answer is the strength of J. If J is weak, you only intersect in 1 place. If J is big enough, you'll intersect in 3 places. So in other words, J measures the strength of complementarity. It determines the slope of the best response function. And this model exhibits a phase transition. If you start J equals 0, the equilibrium is unique. If J is infinity, either everybody chooses 1 or everybody chooses -1. So what happens is you start J at 0 and you start to increase it. There'll be a threshold where if J is above it, there are multiple equilibria. In other words, there's enough complementarity for self-consistent function. Okay, that's just a very, very fast theoretical statement. What we want to know, can we exploit those things? So what I want on the table is the observation that linear social interactions models are theoretically boring. They have unique equilibria. I'm sorry, it's true.
You're right. It's sad.
It's sad, but and it was important to prove it, but bottom line was that's how they are. In contrast, discrete choice models can exhibit multiple equilibria if complementarities are strong enough. I claim, and so that, and this is, that was ideas that came out of Larry's talk, where these notions of uniqueness versus multiplicity. I want to talk about the econometric implication. So let me put it this way. Suppose that I said to you that I was able to make an argument that there are multiple equilibria across groups. That would imply there's complementarity, wouldn't it? Because that's the source of the multiple equilibria. That's our empirical question. In other words, can I make an argument in favor that there's evidence of multiple equilibria? If I can, then that tells me there's complementarity that's big. It doesn't tell me the value of J. And so that's the idea I want to leave with you with, which is that if we're thinking about measuring social interactions, The focus of the identification discussion so far is can I identify the values of the parameters? It may be that there are environments where actually I can't identify the values of the parameters, but I can tell you something about the parameters. I could say the J is non-zero and it's big enough for multiple equilibria. That's a form of partial identification. Everyone with me? So, how can I do that? I want you to think about an example I gave you in the first lecture. I said that I have classrooms and the students, their X's are identical. This classroom, high attainment. This classroom, low attainment. This classroom, high attainment. I'm really picking on my poor Wisconsin student. Low attainment, so on and so forth. I asked you, what would that tell me? Was that evidence of social interactions? Or multiple equilibria? I said, well, maybe it is, but maybe it's just teacher quality. Everyone with me? So that's what I meant when I said that if I have fixed effects, I can't identify anything in fixed effects if I don't say anything about them. I can never tell you whether there's multiple equilibria. Suppose I told you this. Everyone with me? High attainment, low attainment. Beverly Hills High School, richest school district of the United States. Poor school district. Everyone with me? And I told you something else. In fact, I mentioned it. Rich school districts have better teachers on average than poor school districts. Everyone remember that? It's a fact. What would my inference be if they're doing poorly and I'm willing to say that the density from which their teachers come is better, stochastically dominates the density from which her teachers come, yet they're doing better? What's the only explanation left? How could they be doing better than them? High equilibrium, low equilibrium. Yeah, very bad equilibrium. Does everyone see where I'm trying to go with this? What I'm putting on the table is an idea that Brock and I developed. We call it pattern reversals. If you look across groups, suppose that this group has better fundamentals, this has good fundamentals, bad fundamentals. But the performance is the opposite of what the fundamentals say, because they're rich and they're poor. There's two explanations. This model gives us only two candidates for the explanations. Either there's unobservable heterogeneity, the alphas, that explain the reversal, or they're at different equilibria. So the claim was that it might be possible to make an argument that the reason that the fundamental, there's a pattern reversal, is not because of the alphas, it's because they're at different equilibria. And I just gave you the hint for that. I said, if I have, they do worse than them, and I assume that the density from which the teachers are drawn here, first order stochastically dominates the density for the teachers here, then the conclusion is multiple equilibria. If I'm not willing to make that assumption, I can't say anything. That's going to be the basis of actual theorems for the identification of social interactions. And so to play that out, this is what I'm trying to say. So if I have two groups, G and G prime, and I make the observation that the G is doing worse than G prime, even though alpha has better Y's and X's, there's only two explanations in this model. Either alpha G prime is great, or G is at a bad equilibrium. And so here's an example of a theorem. Suppose I have two neighborhoods. Y is higher in this neighborhood than this neighborhood. And I assume that the density of teacher quality, first order stochastically, alphas are the distribution function of the alphas in this neighborhood, first order stochastically dominates this neighborhood. If this neighborhood has higher average outcomes, then I conclude there are multiple equilibria, and hence J is big enough to produce multiple equilibria. So that's an example of a partial identification theorem. Does everyone see the intuition? From the prism of the model, this is model specific. It says this model is true. There's only two ways that you can do better than him when he has better Y's. Either you have a better alpha or you're at a better equilibrium. If I append to this the assumption that the distribution function is quote unquote better for the alphas, that only left the other explanation over. So that's an example of partial identification. Now, let's think about these. And so first of all, notice the standard identification assumption would say that alpha is 0, the density is degenerate, it's at 0. So the assumption here is, rather than say that alpha is 0, which is extreme, it doesn't, on the other hand, it doesn't say alpha can be anything. If alpha can be anything, nothing's identified. Rather, this approach says that we can place a restriction on the shape of the alphas. We call them shape restrictions. We, for example, say that alpha first order stochastically dominates across the neighborhoods. Then we get partial identification. And so what I want on the table is the recognition that one of the routes to identification that so far has not really been implemented is this notion of pattern reversals. When you have outcomes that reverse the rank orders of the fundamentals, multiple equilibria and coordination at different equilibria is one of the routes that could explain that. And so that's a strategy for trying to uncover social interactions. All right, the final result I want to talk about, so that would be one example. Here's a second example. Suppose the alpha is a unimodal. In other words, the density, whatever it is, it's unimodal. Then the question, is everyone with me? Then a question I can ask is, what will be true about the distribution of average group outcomes? So here's a complicated thing. What it says is assume that the density of the fixed effects is unimodal, and assume J is 0. Everyone with me? Then the following is true. If I look at groups at a given level of average behavior, it must be that there's some pi such that the contextual effects, so the net value of the contextual effects is also unimodal. So in other words, if the alphas are unimodal and you look at all the groups where the expected value is 0.4, let's say, there'll be a nice unimodal density of d times y. Therefore, if it were the case that I looked at a given fraction of neighborhoods in which, let's say, 40% of people are doing something, if there's no way to construct a unimodal density of the d times y, it has to be the case there are multiple equilibria. Okay, that sounds really convoluted, but think about what it's saying. If I look at all of the neighborhoods that have 40% doing something, if they have to have a bimodal density of d times y, that means that they're at different equilibria. Some dy's are at this equilibrium, some other dy's are at different equilibria, but they both end up with the same average behavior. Okay, so I know I'm saying that this is a hard word to say, let alone to say it publicly. I look at each of the percentages of neighborhoods. Maybe 40% do this, 50% do this. If I see that there's a bimodality to the y's, that has to be because of multiple equilibria. That the high y's are at the low equilibrium and the low y's are at the high equilibrium. In contrast, if I looked at each of the percentages and have this nice unimodal density around a given y, that's consistent with the j's being 0. Now the reason I wanted to end with that is that Larry talked about the crime and social interactions paper. There's actually a mistake in it. The paper claims that the equilibria for crime rates is unique, and the reason for that is it looks at the average crime rates across precincts, and it says the density is unimodal. Everyone with me? And so their idea was, well, if there are multiple equilibria, you get a bimodal density or a multimodal density of crime rates. That's actually wrong. If there are multiple equilibria, what you would have is a mixture density. Some neighborhoods would be at this equilibrium, some neighborhoods at this equilibrium, some neighborhoods at this equilibrium. There's no guarantee that a multimodal density is, that a mixture density is multimodal. We could have a unimodal density of outcomes, even though it's a mixture density. So some people come from this equilibrium, some come from this equilibrium. some come from this equilibrium. So as a mathematical statement, everybody knows what a mixed shear density is? Mixed shear density says there's two components, the probability alpha from this density, and probability 1 minus alpha from this density. Multimodal, certain probability of this density, certain probability of this density, certain probability of this density. Mixed shear densities are a way to think about multiple equilibria. The neighborhoods are at different equilibrium, some probability from this equilibrium and the probability of this equilibrium. My point is, you cannot say that multiple equilibria create multimodal densities of outcomes. What you can say is that if there are multiple equilibria, then it is possible that you will see very disparate y's producing the same m. And that's what this theorem is instantiating. And so the correct way to try to deal with the modality of the distributions of group characteristics is to see whether, for the same average behavior, you get very disparate fundamentals producing. Because after all, my story was low outcome, high outcome. Here was a different one. Equal outcomes even though he's high and she's low. And that's the different route to partial identification. So, upshot. Discrete choice models exhibit sturdy identification problems. In other words, the reflection problem type stuff doesn't occur, and you can even identify for binary choice cases the density of the errors. The reason for that is that these models, because they're conditional probabilities, are intrinsically nonlinear. And so for reasons we talked about in the first half of the lecture, all that works out. That's idea one. Idea two, as theoretical objects, they have something new. They produce multiple equilibria, and multiple equilibria can be exploited for forms of partial identification. Is that the last thing I'm saying in the lecture? I thought I had more things to say. I guess I'll have to stop. Anyway, okay, so the serious point is the following, and that is a whole area that has not really been explored yet is to understand partial identification of social interaction effects exploiting multiple equilibrium properties. So just as the endogeneity of social structure can be our friend, it can help with identification, what I've tried to demonstrate here is that multiple equilibria can help with identification. In much of the econometrics literature, multiple equilibria is a problem for identification. But those are games of strategic substitutes, not complementarity. So the IO entry stuff, that's a very different environment here. So, I think I saw the new tree. There you go. Okay, so really what I want to end on the table is, if you look, I will do a little bit of self-promotion. So Larry and I and Buzz Brock and SENDs have a handbook of social economics chapter, identification of social interactions, which talks about a lot of this stuff in much more detail. And it also outlines ways to proceed to think about discrete choice models in which they're two-stage games. First you choose the group, then you choose the behavior, and those types of models, identification is still an open question. So I think it's an exciting area for doing. So let me stop there.